So, what do you think the speed of this car is? No, I don't mean speed in this car, although that is a pretty scary thing to think about. I mean the speed of the car itself. Now, that's one of the many things we're going to be talking about in today's video about AP Physics C Mechanics, specifically Unit 1, where we're going to be talking about kinematics. Now, some of the objectives for today are we're going to first be talking about position, velocity, and acceleration. Then we'll talk about objects in freefall and also objects in projectile motion, before finally covering how they move in uniform circular motion. So first, let's give ourselves a brief intro to what kinematics actually is. Now, kinematics is the study of how an object moves in terms of its position, its velocity, and its acceleration. But what does that even mean? So, position is where an object is at a given time. For example, this circle right here could be at position 0, could be at position 2, could be at position 6, and so on and so forth. Now, the velocity is how fast the object is moving. For example, if this ball is at position 0 and then every second it moves one spot over to the right, the velocity would be 1 because it's moving one spot to the right every second. Now, if the object moves backwards, its velocity would be negative because it's moving backwards. So in this case, it would be -1. Now, the same thing works if the object is moving up and down. So if the circle was moving up, its velocity would be positive, and if it was going down, it would be negative. So what's acceleration? Well, acceleration is how fast this object's speed is changing. So the way this works is, let's say our object is at 0, and then in the first second, it moves one spot. But in the second second, it moves 2. And in the third second, it moves 3, and so on and so forth. In this case, the acceleration of our object would be 1, because after every second, the velocity of the object increases by 1. Now, the same thing works here as well. Let's say in the first second, it moves 3, and then in the second second, it moves 2, and then 1. In this case, our acceleration would be -1 because the object speed is decreasing by 1 every single time. Now, speed in this case is the absolute value of velocity. So no matter whether the object is moving forwards or backwards, speed will always be positive. And so with this in mind, let's talk about our first big topic for today, which is average velocity. Now, average velocity kind of gives us like an estimate of how fast we're going at any given time. And to calculate this, we use the total distance traveled and the total time that has elapsed. For example, it takes a car 13 seconds to travel 95 meters. What was its average velocity? And so this is a pretty simple problem. All we do in this case is we put 95 over 13 to get our average meters per second, which is approximately 7.31. Now, a more difficult application of this would be instantaneous velocity, which is the velocity at a single instant in time. Essentially, because objects sometimes don't speed up and slow down at a constant rate, the velocity might be different at different points of the distance. And so the way we calculate this is through these relationships. Because the rate of change of position is velocity, velocity is the derivative of position. Now, if you're confused about what this means, I'd suggest you look at our AP Calculus AB reviews where we talk exactly about what rate of change and what derivative are. But for now, let's just keep this in mind. And the same thing works for velocity and acceleration. Because the rate of change of velocity is equal to acceleration, acceleration is the derivative of velocity. So keeping these in mind, we can now calculate instantaneous velocity. So let's look at this example. If the position of a car is given by the following equation, we're forced to find the velocity at time t equals 3. So what we do in this case is we realize that, again, velocity is the derivative of position, as we said right here. And so if velocity is the derivative of position, all we need to do is take this position equation, take the derivative of it, and that should give us our velocity equation. And so that's what you do right here. And when this is our equation, all we have to do now is plug in t equals 3, and our final answer is 0 meters per second. Now, just for a quick aside, what does 0 meters per second actually mean? Well, if the velocity is equal to 0, it means the object isn't moving. And in physics, we call this at rest. So whenever you see something in a question that says an object is at rest, just know its velocity at that time would be equal to zero. Now, this makes a big comeback in our next topic, which is objects in free fall. But first, let's again have a quick aside. Now, I'm sure we all know of this guy named Isaac Newton, who one day sat under a tree and discovered that because an apple had landed on his head, gravity exists. Now, I don't really know how he came up with that conclusion in such a short amount of time, but this is the basis for the theory of objects in free fall, which basically describe the motion of any object that is dropped off of a tall tower or thrown up into the sky. Now, for all of this kind of motion, there's one thing that is important to keep in mind, and that is the acceleration due to gravity is always going to be negative 9.8 meters per second. And because acceleration in this case is constant, we're able to use simply the fact that acceleration is always equal to this in order to derive equations for velocity and position. And so, like we stated earlier, velocity is the derivative of position. So position is the antiderivative of velocity. Similarly, because acceleration is the derivative of velocity, velocity is the antiderivative of acceleration. Now, again, if you're confused about what antiderivative means, I'd suggest you look at the AP Calculus AB reviews. But using this information, we can derive all of these equations that we use for free fall. So because acceleration equals negative 9.8, when we take the antiderivative of that, our velocity equals negative 9.8 t plus v naught. And v naught basically is the initial velocity if there is any. Now, the position equation is when we take the antiderivative of that. And that's given by this equation. Again, y naught is just the initial position at that instance in time. So the same equations can actually work for any kind of acceleration, even if it's not negative 9.8. Simply, if we replace negative 9.8 with a random constant acceleration a, we have the same equations that can be used for any kind of calculation. So for example, let's say an apple is dropped from rest at the top of a 40-meter tower, and we're asked what is its speed before it hits the ground. Now this situation kind of looks like this. We have a tower that's 40 meters tall, we have an apple at the top of it, and we know that because it's dropped from rest, it's dropped with an initial velocity of 0. And our goal is to find the final velocity. So after it travels all of that distance, what is v final? So to solve this, we first have to look at the position equation for this situation. Now, because this is a situation of free fall, our acceleration is going to be negative 9.8. And so we plug everything we know into this equation to solve for time. And when we solve for time, we get time is approximately equal to 2.857-ish seconds. And the reason that we keep 6 decimal places is because we're going to be using this answer to calculate the velocity. And the way we do that is we simply just take the velocity equation and plug in what we know there as well. And when we do that, we get the velocity equals at plus v naught. We plug in acceleration and the time, and then our initial velocity is just 0, so we disregard that, and we get negative 28.0 meters per second as our final answer. Now, we went through a bunch of steps to calculate this, and sometimes, because we don't really need to know the time in this equation, there's another equation that we can use to solve this, and that's called the two velocities equation. And for this, it's simply the final velocity, or a velocity at any point in the interval squared, is equal to the initial velocity squared plus 2 times the acceleration times the distance traveled. So let's try the same example above with this equation. So for this, again, we use the same equation, and we isolated v1, and to do that, there's just some simple algebra steps, and we get negative v1 equals the square root of 2 times the acceleration times the distance. And when you calculate v naught, you get the same answer, which shows that we did this in so few steps, and we did this in so many steps. So sometimes, if it's possible, we could use the two velocities equation instead of all of these kinematics ones. So let's use a second example, which is going to be an object that's thrown upwards from the ground. So in this case, we're asked an object is thrown straight upwards from the ground with an initial speed of 22 meters per second. at what time does it reach maximum height? So in this situation, we kind of have a similar dilemma. We have an object that's launched up and it goes up and then it comes down. And so in this one, we have to try to find when it reaches maximum height, which is at the top of this curve right here. And so to do that, there's one relationship that we need to keep in mind. When an object is at the top of a curve, its velocity is always going to be zero, especially when it's in a free fall, which means that we can just use our equations for velocity and set vt equal to zero and v naught equal to the initial speed right here. And so that's what you do, because we're trying to solve for the time at which velocity equals to zero, we set velocity equal to zero, plug in acceleration, leave t as a variable, and then plug in our initial velocity. And we get that the time equals 2.24 seconds. And so again, for a quick sanity check, that's how long it takes for this object to reach from here to here. Now, here's some quick notes about freefall. Again, acceleration in freefall is always going to be negative 9.8 meters per second squared. And that's something that you should always keep in mind. Another thing is when velocity and acceleration are the same sign, which means if they're both positive or if they're both negative, an object is going to be speeding up. And if they're different signs, the object will be slowing down. Now, this is really important just to make sure you're on the right track when you're solving problems and to make sure your answers actually make sense. And the last thing is what we just covered. At the top of a curve, because the object is changing directions, v naught or v will always be equal to zero. Now, changing directions means that it's going up and then now it's going down. And whenever a direction change happens like that, velocity always has to be equal to zero. Now, this is explained more also in our AP Calculus videos if you want to check that out. But for now, that's all you basically need to know for free fall. Now, the second kind of motion we're going to be talking about today is projectile motion. And that's usually when an object has a certain initial velocity at an angle. So for example, it could be an object that's sliding off a table and falling to the ground, or an object that's launched at an angle and falls back to the ground. Now, some notes for projectile motion are as follows. Acceleration is in both the x and the y directions. Now, this means that for each of these objects, it's moving both in the x direction and in the y direction, because it's moving some distance forward while it's moving down. And the same thing can be applied to this one as well. The object is moving partially in this direction and partially upwards. Now, what does this mean? This means that when we calculate the equations, we can no longer use these same equations that we derived here. Instead, we have to derive new equations that we can use separately for x and for y. So first, let's look at x. Now, the acceleration in the x direction is always going to be equal to zero, which means that velocity is going to be not v naught, but v naught cosine alpha, with alpha being the angle that it's launched at. For example, in this case, the angle at which it's launched at would be approximately like around 30 to 45 degrees, which will be specified in the problem. But you would use that angle measurement when you calculate velocity because part of the velocity is in the x direction, and again, part of it is in the y direction. And so when we take the antiderivative of that, we get this following position equation. Now, the same thing can be said for the y acceleration, and this looks pretty similar to our old equations that we already used. Now, acceleration here is going to be negative 9.8, and velocity is pretty similar to, again, the equations that we covered, except for the fact that it's v naught sine alpha instead of v naught as like plain v naught. And the same thing is for the y position equation. It looks pretty similar again to the kinematics one, except for the fact that there's a sine alpha in here. And just keep in mind that x is cosine and y is sine, and not to get those two mixed up. So I know that was a lot of information, but let's just go through a quick example. So an object is launched from the ground at exactly a 45-degree angle. So it starts here and then it goes up at 45 degrees with an initial velocity of 8 meters per second. Now the object returns to the ground shortly after. Again, this is the path that it follows. So how far has it traveled along the x-axis? So the first step here, and projectile motion questions are often multi-step problems. So the first step here would be to find the time that the object reaches the ground. And to do this, we look at the y position equations. So again, we substitute what we know. So we know that it starts and it ends at the ground. So we plug in 0 for both of those. And we know, again, our acceleration divided by 2. And then we also know our initial velocity and our angle. And we're trying to solve for time. And when we solve all of that, we get the time is approximately equal to this value right here. And now that we use the y equation, now we need to use the x equation to figure out how much it's actually traveled along this x axis. And to do that, we just use the x position equation, we substitute what we know, and we get that the object travels approximately 6.53 meters. Now, that was a lot of information about how objects kind of move both in free fall and as projectiles. But finally, let's talk about objects that move in a circle. And specifically, we're going to be talking about uniform circular motion, which means that an object travels in a perfectly circular path and at a constant speed. Now, again, for a quick sanity check, constant speed means that there is no tangential acceleration. And tangential just means no acceleration along the circumference of the circle. Because it's traveling at a constant speed, when we take the derivative of any constant, it's always going to be equal to 0. But circular motion does have one type of acceleration, and it's called radial acceleration. And radial acceleration is basically the force or the acceleration that's pointed toward the center of a circle. And what that acceleration does is keeps the circle on its path. Now, for example, in all cases, the velocity vector or the direction of motion of the sphere will just be pointing towards the tangential rim of the circle, which means when the object is here, it's going to be pointing this way. And so to keep this object from straying out of its orbit, there has to be some sort of radial acceleration pulling this circle into the circular motion. And that's what a rad or radial acceleration does. And so the way to calculate radial acceleration is using these two equations. You can either take the speed squared and divide it by the radius, or take 4 pi times the radius divided by the time it takes to complete one circular path. And which equation you use just depends on what information you're given with the problem. So, for example, let's look at this problem. A train travels in a circular path with a speed of 56 miles per hour. If the track has a radius of 120 meters, what is the train's radial acceleration? Now, with a problem like this, it can be really easy to just go 56 squared divided by 120. That's going to give me radial acceleration, right? But we have to be careful about units. In this case, we're given miles per hour. And so we're going to have to convert that to meters per second for us to actually have an accurate answer. And to do that, we just do some simple conversion. We have 56 miles per hour, we multiply that by 1 hour, or by 3,600 seconds per hour, and then by 1,609.34 meters per mile. And when we do all of these calculations, we get that it has a speed of approximately 25 meters per second. And so when we plug that into our equation for a rad, or radial acceleration, we get 25-ish squared over 120, which gives us approximately a radial acceleration of 5.22 meters per second squared. And radial acceleration has the same units as acceleration, which is just meters per second squared. And now we've covered not just projectile motion and kinematics, but also uniform circular motion. And so when we go back to our learning objectives, let's look at what we've covered today. So the first thing we covered is position, velocity, and acceleration, and how they're all related. Again, velocity is the derivative of position because it's the rate of change, and acceleration is the derivative of velocity, again, because it's its rate of change. We used that to determine the equations for objects in free fall, where we talked about how the gravitational acceleration is always going to be negative 9.8, and how that governs how we find the relationships between the equations for position, velocity, and acceleration for objects in free fall. Again, free fall means it's either thrown off of a building or thrown up into the air. Now, the third thing we talked about was projectile motion, or if an object is launched at a certain angle and with a certain velocity. Now, in this case, we learned that an object both has an x direction and a y direction. And for each one of these, it has different equations that we use. And finally, we talked about uniform circular motion, or how an object behaves when it's in circular motion. Now, next time, we're going to be talking about Newton's laws of motion in Unit 2 of AP Physics. Thanks for watching.